Hello Calc 3 and welcome back to another video. So in this video we'll be covering section 16.1, the beginning of chapter 16, and we'll be covering line integrals. So for certain problems we need a more general notion of the integral than the integral that we defined in Calculus 1. And in these particular cases we need to integrate over a curve rather than over an interval from a to b, like we did in Calculus 1. And these more general integrals are called line integrals, and they're the subject for the video today. So let's get into defining what these line integrals actually are. So suppose that we have a function f of x, y, z. It's a real valued function, so it pops out real numbers. And we wish to integrate the function over a curve c as opposed to some interval within the domain of f and parameterized by the curve or the vector valued function r of t is equal to g of t I plus h of t j plus k of t k, where t is ranging from a to b. So here we have that g, h, and k are component functions for our vector valued function r. Then we can partition our curve c into a finite number of subarcs. So if you look at the diagram that I have in the bottom right here, we're partitioning our curve in blue into a bunch of subarcs that are denoted by the dashes that are on the different lines here. And the typical subarc is going to have a length of delta s sub k, or at least that's what we will denote it. So again, if you look at this particular point that's been picked inside of the interval on the curve there, we have the length of that interval on the curve is denoted delta s sub k. And after we choose a point for each of these intervals, and again we denote the point by x sub k, y sub k, z sub k, then we can form the following sum, which resembles the Riemann sums that we've been talking about in the last chapter. So we have s sub n is equal to the sum from k equals 1 to n of f of x sub k, y sub k, z sub k, times delta s sub k. So we have the function evaluated at each of the points along the particular subintervals of the curve here, multiplied by the arc length of those subarcs. And again, this is similar to a Riemann sum, but delta s sub k represents the change in arc length as opposed to the change in x, like we would see in Calculus 1, where we're integrating over just an interval from a to b. And if our function f is continuous, and if the component functions g, h, and k have continuous first derivatives, then we can conclude definitively that the limit as n goes to infinity of these sums s sub n is going to exist. And it is understood here that when we say the limit as n goes to infinity, it implies that the length of each of these subarcs is going to 0. So delta s sub k is going out towards 0 as n goes towards infinity. And this leads us to our definition of the line integral. So if f is defined on a curve c, given parametrically by r of t is equal to g of t I plus h of t j plus k of t k, where t is ranging from a to b, then the line integral of f over that curve c is the integral, and notice here that we have this sub c here, similar to what we did for double integrals with the regions. So we have the integral of f of x, y, z over c ds. Notice that we're integrating with respect to the arc length parameter here, is equal to the limit as n goes to infinity of those sums s sub n from before. So we have the sum from k equals 1 to n of f of x sub k, y sub k, z sub k times delta s sub k. So if c is a smooth curve, meaning that the derivative exists and is not equal to 0 anywhere along the parameterization, so from t is equal to a to t is equal to b, and if f is continuous on the curve c, then this limit exists. Okay, and now a little piece of information from section 13.3. So remember that the arc length is given by s of t is equal to the integral from a to t of the speed, or we can say the magnitude of the velocity function, d tau here. So again, we're just using d tau because we use t as one of the limits of integration. And remember, this is the arc length along the curve starting at the value a here. So if we write this equation that we have from section 13.3, then we can use the fundamental theorem of calculus to say that the derivative of s with respect to t is just equal to the function in t giving the speed, or just the magnitude of the velocity function. And this tells us that ds can be written as the magnitude of the velocity function dt. And we can use this fact as well as the definition that we have up here, and now we can write down an equivalent expression for the line integral. So the integral of f of x, y, z ds over the curve c is equal to the integral from a to b of f of g of t, h of t, k of t. So here we're taking our function f and we're writing the variables x, y, and z as they are in the functions with respect to t, and then we're writing ds as the magnitude of the velocity function dt. And so now this integral that we've written on the right side of the equation here is just an ordinary integral in the variable t. So we've taken the definition for the line integral, which is given in ds here, and now we've written it as an integral in one variable. So this is just an ordinary integral that we could evaluate using methods from Calculus 1. Okay, so now that we've built up the notion of the line integral, we can move on to how to calculate these things in practice. So every time that you're given a question about a line integral, there are really two things that you have to do here. You're going to be given some curve C, and for that curve, you have to find some smooth parameterization of the curve that looks like r of t equals g of ti plus h of tj plus k of tk. Or if you're working over curves in the plane as opposed to space, then it would just be g of ti plus h of tj. Notice that these are just vector valued functions that are tracing out your curve. And then secondly, you want to evaluate the integral as using this equation that we just developed up here. So we can write the line integral of f of x, y, z over the curve c is equal to the integral from a to b of f of g of t, h of t, k of t times the magnitude of the velocity function dt. So again, we're taking that integral with respect to t, and that's just a regular ordinary integral. Also note that this function f of g of t, h of t, k of t can also be written as just f of r of t. So the intuition is there, or the intuition there is that f of r of t just means that we're taking points that are on the curve and plugging them into f. Okay, so let's move down to our first example here. Let's say we want to integrate the function f of x, y, z is equal to x minus 3y squared plus z over the line segment c that joins the origin to the point 1, 1, 1. So again, we use this methodology above. So we start off by finding a parameterization for the line segment c. But we did that in chapter 12. So we found parameterizations for line segments. We have to find a vector that is parallel to the line segment and then find a point that the line segment contains. So using the fact that the line passes through 1, 1, 1 and the origin, we find that the vector 1, 1, 1 is parallel to the line segment C. And we also know that C contains the origin, so that'll give us a parameterization right away. We can write C is r of t equals t times I plus t times j plus t times k, where t is running from 0 to 1. And after that, we want to find a function for the magnitude of the velocity. So again, the velocity is going to be the square root of the squares of the derivatives of each of the component functions. So if we take the derivative of t for ti, we get 1. If we take the derivative of t for tj, we get 1. If we take the derivative of t for k, then we also get 1. And so the magnitude of the velocity is just going to be the square root of 3 all the time with the parameterization that we've chosen. Also, if we look at f of r of t here, so we take each of these component functions and we plug them in respectively to x, y, and z in our function up here. Then we get t minus 3t squared plus t. And at this point, we're ready to write down the equation for the integral. So the line integral of f of x, y, z over the curve c is equal to the integral from 0 to 1. So the 0 to 1 comes from our parameterization, because t is between 0 and 1, of t minus 3t squared plus t, so that's f of r of t, multiplied by the square root of 3, which is the magnitude of the velocity, dt. And at this point, it just becomes a problem from Calc 1. So we're just solving this integral here. We can pull the square root of 3 out, and we're left with 2t minus 3t squared. And that'll give us a square root of 3 multiplied by t squared minus t cubed, evaluated from 0 to 1, which ends up just being 0. So now we can move on to another little bit of a fun fact here. So it's the additivity of the line integral. If we have a curve C that's made up by joining a bunch of smaller curves together end to end, then the integral over the whole curve C is going to equal the sum of the integrals over each of the smaller curves that compose C, which I called C sub I. So another way to write this is the integral of f of x, y, z over the curve C is equal to the integral of f of x, y, z over C1 plus the integral of f of x, y, z over C2, and so on, all the way up to the integral of f of x, y, z over C sub n. So this is the generalized notion of the additivity of the integral from Calc 1. So remember that if we had an integral like this, then we could write that as the integral from a to c plus the integral from c to b, something like that, where c is going to be a point between a and b. So this is, again, the generalized notion of that fact to the line integral now. And we can move on to our second example then, using this fact. So let C be the path from the origin to 1, 1, 1, but this time the path is going to be a little bit different than what we did in the last example. So the path is going to consist of the line segment from the origin to 1, 1, 0, and then the line segment from 1, 1, 0 to 1, 1, 1. So it's going to look something like this, whereas our last curve went straight from 0, 0, 0 to 1, 1, 1. And again, we want to integrate the same function, f of x, y, z is equal to x minus 3y squared plus z over the curve C. So our curve here, C, is going to equal the first curve union with the second curve. So this would be C1 and this would be C2, and the curve C is going to be both of those together. So C1 we can parameterize as r of t equals t times I plus t times j plus 0 times k, where t is going from 0 to 1. And the second curve we can parameterize as r of t equals 1i plus 1j plus tk, where t is going from 0 to 1. And if you want to, you can just stop the video and check that both of those parameterizations work. And by this additivity fact that we had above, we can write the integral of f of x, y, z over c as the integral of f of x, y, z over c1 plus the integral of f of x, y, z over c2, and then we can solve both of these integrals. So if we're looking over the first curve, we get the integral from 0 to 1 of t minus 3t squared. So here we're taking t, or we're taking our parameterization r of t up here, and we're plugging it into the function f of x, y, z. And this gives us a t minus 3t squared and the magnitude of the velocity is going to be the square root of 2 in this case. And then for the second curve, C2, we get the integral from 0 to 1 of 1 minus 3 plus t, and in this case the magnitude of the velocity is just going to be 1, so we don't have to even write it there. And now we can solve for both of these integrals here. So we get the square root of 2 times 1/2 t squared minus t cubed evaluated from 0 to 1 for the first integral. For the second integral, we get minus 2t plus 1/2 t squared evaluated from 0 to 1. And again, if you do a little bit of algebra here and you just solve for both of these things, you end up finding that ultimately the line integral over c of our function is equal to negative the square root of 2 over 2 minus 3/2. And notice here, so first off, this example used the additivity of the integral, so we had different piecewise smooth curves that were composing our big curve C that we were interested in. So we had to use additivity in this case, but more than that, the paths that we chose from 0, 0, 0 to 1, 1, 1. So in both examples, we were looking at paths that went from one point to the same point. In example 1 and example 2, the different paths that we chose changed the value of the integral, and this is often the case. So you can have one path from the origin to 1, 1, 1 and another path from the origin to 1, 1, 1, such that when you take the integral, you're going to get very different values. And there are all kinds of different paths that you could take from one point to another. So the line integral has a richer set of solutions, maybe I would say, if you're taking the integral from one point to another, because the path that you take often matters. And once we get to section 16.3, we'll talk about the cases when the integral is independent of path, but we'll wait till we get there. And again, I just boxed this in because it's an important fact. The value of the line integral along a path joining 2 points can change if you change the path between them. Okay, and now finally let's move on to the last example then. So let's say we want to find the line integral of f of xyz equals 2xy plus the square root of z over the helix, which is parameterized as r of t equals cosine ti plus sine tj plus tk. And in this case, t is going to be going from 0 to pi. Okay, so we're going to use the same methodology we did before. So we can find the velocity first just by taking the derivative of each of the component functions of r here, and we get negative sine ti plus cosine tj plus 1k. And then if we take the magnitude of that velocity function, we end up with a sine squared and a cosine squared that are going to equal 1. And so ultimately this is equal to the square root of 2. And now we can write the line integral f of xyz over c is equal to the integral from 0 to pi. So here we're just using the parameterization that was given to us in the problem of f of cosine t sine tt multiplied by the square root of 2, because that's the magnitude of the velocity, dt. So we can take cosine t, sine t, and t and plug them in for the appropriate variables in the function f of xyz. And that'll give us this 2 times cosine t sine t plus the square root of 2. And again, we're still multiplying by the square root, or I should say the square root of t. And again, we're still multiplying by the square root of 2 here. We can use a trig substitution here. So 2 times cosine t sine t is just equal to sine of 2t. And at this point, we should be ready to just solve this integral. So we've reduced it to a problem from calculus 1 at this point. We end up with the square root of 2 times negative 1/2 cosine 2t plus 2/3 times t to the 3/2 evaluated from 0 to pi. And you can take pi and you can take 0 and plug them in for this expression here. And at the end of the day, we end up with this value over here. So we end up with 2 times the square root of 2 divided by 3 times pi to the 3/2. So in this example, the parameterization of the curve that we're interested in was just given to us right away, which actually takes one of the steps out of the process for us that we don't have to worry about. Okay, and then just a final comment. So again, this video is not super long. Many of the other sections inside of this chapter are going to be much longer, so just be prepared for that. But fortunately, this video is a little bit short. So in the case that we're looking at line integrals in the plane, as opposed to line integrals in space, as we have been up until this point, there's a really interesting geometric interpretation that I should probably tell you about, because hopefully this will solidify the idea of what's going on here. So if C is a curve in the plane as opposed to space, so we can just parameterize C as R of t equals x of t I plus y of t j, because there's no k component here, and t is ranging from A to B, then we can generate a surface in space by dragging a line that comes out of the plane along the curve. So if you look inside of the diagram that I have down here, you can think, what I mean here is that we start at A, for example, and we keep drawing these lines that are coming out of the plane, like this one, as we move along the curve in the plane. And if you think about it, just think about those lines extending forever. Then this is going to make kind of a big wall inside of space that's curving. The one that's given here looks kind of like a tail, but don't worry about that yellow line on top yet. I'm literally just talking about the wall that extends up forever from here. And now, if we have that curve in the plane, and we have another function z equals f of xy that defines a surface in space above the xy plane, then we can talk about the portion of that wall that we've just created that's underneath that surface z equals f of xy. And the line integral is going to tell us something very interesting about that wall. So in this case, the line integral, which is denoted the integral of f over the curve C here, describes the area of the wall over the curve C that's bounded above by z equals f of xy. So again, we're drawing a wall that follows along the curve C and extends up in the z direction forever. But then we have a surface, and that's going to cut off the wall at some point and bound our wall. And the line integral is giving us the area underneath that curve in space, or the area of that wall. So you can hopefully see how this is an interesting generalization of the notion of the integral from Calc 1, because the integral from Calc 1 was just the area under a curve, as long as the curve was positive, always above the x-axis. And in this case, we're still kind of talking about areas under the curve if we're looking at line integrals for curves in the plane. But this time we're free to actually choose a path throughout the plane and then create this yellow curve that's running along our surface, and we can evaluate the area under that curve. So this is kind of what we would mean by a generalization of the integral from Calculus 1. The line integral is going to end up being significantly more powerful than the regular integral from Calc 1. Okay, so that's the end of the information for section 16.1. All of the homework for the rest of chapter 16 is already on Blackboard, so if you want to, you can work ahead on that. And I'll work on getting section 16.2 out probably by Monday, is what I think.